the first problem we're going to look at is the following. It is known that in some physical phenomenon, the energy and the pressure and the area are combined in a law, in a homogeneous law, and we are asked to show that this relation on the right-hand side is true. So let's get to work, okay? So the first thing is first. The first thing we're going to do, we're going to decide what are the dimensions of the energy, pressure, and area, and figure out which are the fundamental units appropriate, or the ones that are showing in this problem, okay? So now the energy is measured in kilogram meter squared per second squared. So that would be like mass, length at power 2, time at power -2. And then on the right here, I'm gonna kind of record the fundamental units that are showing up in this problem, okay? All right, so that's with the energy. Then the pressure, right? The pressure is measured in kilogram over length over second squared, okay, over time squared. So it's kilogram, length at -1, time at -2. Okay, so up to now, what fundamental units do we have? We have mass, we have length, we have time. And I think that would be all, because the next one is the area, and area is easy enough, right? It's just length squared. That's squared. All right. So now this relation that, well, I have a cat playing there. That's what is going on. Okay. So the relation that is given, let's call it the relation 1. So from, from EPA equals 0. We know that, we know that. Okay, there are 3 numbers, okay, such that if we combine the dimensions of the physical objects that show up in this, in the description of this phenomenon, okay, okay, that's a C there. Let's see, equals, right? Whatever fundamental units are showing up in this problem. So in this case is mass, length, and T, all at power 0. I'll take a break to kick the cat out. Okay. How do I do this? I don't know how I'm doing this. Okay. I'm back. Okay. All right. I should have said I'll be back. Okay. So now what we're going to do, we're going to substitute the dimensions of E, right, M, L at 2, T at -2, in terms of the fundamental dimensions. So here they are, M, L -1, T -2B, and finally L at 2, and then at C. So all this stuff has to be M at 0, L at 0, T at 0. Okay, so now we're going to combine the powers, right, for each of the fundamental dimensions. So M, right, the mass shows up at power A plus B, and that's it. Now L shows up at 2A minus B plus, oh, why did I put there A? This is a C there, right? Okay, plus 2C. And finally, time shows up at minus 2A minus 2B. And all this stuff has to be M at 0, L at 0, T at 0. Okay? So now what I'll do, right? We're gonna equate each power with what it has to be, each of them, right? It's a power 0, right? So it has to be 0. I'm just trying to choose some colors here. There you go. So we get the linear system. All right. So let's write this linear system. Okay, actually I have it here. So it's A plus B equals 0. And then 2A minus B plus 2C must be 0. And then minus 2A minus 2B must be 0. Okay. If we're to write the dimensional analysis matrix, right, you know, however you call that one, that A matrix from before, right, so it would be attached to this linear system. Right, this would be something like this: 2 minus 1, 2 minus 2 minus 2, 0. And obviously here we have right, the dimension of A, or M, is the number of columns, okay, which is also the number of unknowns, okay. And then if we're doing the, what is the rank of A, well, in this case, so I'm putting, you know, so okay, so number of unknowns is 3 here, yeah. So the rank of A, if we're to compute it, okay, you're going to see the determinant of A is 0. So, you know, or if you want to do row reduction or however you want to do it, the point is that the rank of A will turn out to be 2. And it's easy to see that this block here has determinant non-zero. Okay, so this was called K, it's 2. So a priori, I know that this system has one independent variable, right? So in this system, we will have one independent. So how do I get this one? We'll have M minus K, which is 3 minus 2, which is 1, is the number of independent variables. All right. All right. But this is like a side note. What happened? What happened? Okay. 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 Yeah. Okay. All right. So as I was saying, A is the matrix that defines the linear system for A, B, and C as unknowns. The number of unknowns coincides with the number of columns, which is 3. The rank of A, if we're to compute it in this example, turns out to be 2. So we know a priori that we have one independent variable. Now, long story short, the point is that we have to solve this system. And as I was saying, you know, you can easily see that the first and the last equation, so this one and this one, they're the same. The second one is the first one multiplied by -2. So it doesn't give us any new information. So then, you know, I can reduce the system to two equations with three unknowns, but one of the unknown will be allowed to be whatever it wants. So here a plus b is 0, and then 2a minus b will be minus 2c, where c is some real number, yeah? There you go. Okay. And now we're gonna solve the system up. So let me write it again here, right? So however you wanna solve it, okay, where c is in R, we want to end up with a equals, so I have it here, minus 2 over 3c, b equals 2 over 3c, where c can be anything. All right, so now we know, okay, so we know that we have right, for every triplet of the form ABC equals, so for any ABC equals minus 2 over 3C, 2 over 3C, and C, where C is in R, okay? We have, okay, E at A, which I'll write it directly as minus 2 over 3C, times the units of pressure at 2 over 3C, okay? Let's make it nice. And the units of area at power C equals, it's 1, but it's basically right, a non-dimensional quantity. It's a scalar. All right, so this being said, I'm gonna go back to the problem, to the initial problem and, or initial phenomenon, right? So we had F in E, P, A equals 0, and we got, you know, those number of independent variables to be 1. So by the Buckingham pi theorem that we did last time, okay, or 2 times ago, the law, okay, or the relation, okay, and let's call it, did we put a name on it? If not, here, let's, relation 1 is, relation 1 by the Buckingham, okay, relation 1 is equivalent, okay, to some f of pi equals 0, where pi equals E at minus 2/3 C, P at 2/3 C, and A at C is add an a-dimensional quantity. An a-dimensional, meaning it doesn't have dimensions, quantity. Okay, so i.e., that is F in, so now I'm going to substitute those pairs, and that's happening for any C, right? So for any C in R, right? We can choose C whatever we want, okay? So in other words, F at, now I'm going to do some algebra there, P at 2/3 C, A at C over E at 2/3 C equals 0, right? So this little f in EPA equals 0 as a law from physics by doing the dimensional analysis and applying the pi Buckingham theorem, because we got just one independent variable, then is equivalent, this relation is equivalent to another relation in which instead of 3 variables, we have just one. And that one is the combination of the 3 physical objects that are given in the initial description of the phenomenon in question, right? So we have just one pi, not totally. So this pi is like an x, okay? So it's just a notation. It's the letter pi. I'm not thinking about pi as 3.14 or, you know, the ratio in between the length of a circle and its diameter. No, it's just a letter that we're using. I could use x, I could use c, okay? So, you know, traditionally they use pi, we use pi as well. Fine, okay. So we don't know what this f is, this f being the capital F. I don't know what it is. S, we don't know what this one is, okay? But it's irrelevant in what we want to choose, right? When you want to prove. So we want to prove, remember that somehow what shows up inside here is a constant. Now let's think about this relation for a second. So what we have here is nothing else but something that is like an equation in which you have f of x, so I'm going to put it in between quotes, something like an f of x equals 0, right? And I'm going to ask you, what is x? Well, I don't know what is x, but whatever is x is a number, right? So I'm looking for the roots of the equation f of x equals 0. Now that if we assume that this equation has roots, could have 1, 2, 5, I don't know how many, okay, then we'll have, right, some roots. So we have the x equals, I don't know, 5 or a number, right? So I'm going to say x equals x naught, okay? We could have x1, x2, it could be 5. I don't, because I don't know what the law is. The point is that if we take one of these roots of this equation that I wrote in green, f of x equals 0, right? Will be a number. Now let's think about the roots of this original guy. So it should be, there is at least, so more precisely, we assume that this equation has at least one root. What would be that root corresponding to? Oh, is the combination of the physical objects there that they're inside, they're describing the initial phenomenon, the one on the top, right? This guy here, okay? So we assume, right? Our main assumptions is that we assume, right? But, you know, I could say something like, but we assume that this equation, okay, has at least one root, okay? And I repeat, this assumption is nothing else but something equivalent to the initial assumption that this phenomenon is described by this law up here, right? By this guy, right? It is the same thing. So I think, oh, there should be a law, but there should be a law in algebraic terms. Essentially, is like, oh, there is a combination of EPA that, you know, when you put into F, you know, they're like the roots of F of EPA equals 0, right? But then, okay, coming, we know we do dimensional analysis, we end up with an equation in one variable. Essentially, we're assuming that that equation has at least one root. So, okay, this one has at least one root, not roots, okay? This equation has at least one root. Okay, let's call it, I don't know, C, right? It's a number. It is a number. I don't know what it is, but it is a number, right? So then this means that from this equation, let's call it number 2, we end up, if we consider that root C, we get that P at 2/3 C times A at C over E at 2/3 C equals C, right? Oh, I put the C. Okay, let's pull it, let's call it K, constant. It's a constant, it's K. There you go, K. All right. So from relation 2, we get that P at 2 over 3C, A at C over E at 2 over 3C is a constant that we call K. By the way, this constant, okay, I'll just make it here as an observation. This constant depends on the value of C, right? So for every C, we're gonna get a different constant, but that's irrelevant. It's just, you know, it's for completion of the thing. All right, so now I'm gonna flip the page. So where are we? We are that we can write that P at 2/3 C, A at C over E at 2/3 C, right? Okay, is a constant for, it depends on C, right? The point is that is a constant for any C in R. And now let's remember what we were asked to prove. We're asked to prove that, where is it? Here. PA at 3 over 2C, okay, PA 3 over 2 over E is a constant. Okay, fine. So we have to choose now that little c in order for this relation to become that one. So I'm going to choose C to be 3 over 2. Why? Because on the bottom, since we have to prove, okay, that P A at 3 over 2 over E is a constant. So basically, I'm choosing this 3 over 2 here so that, right, when I multiply it there, E becomes a power 1. And of course, everything falls into place if the calculation is correct. So, okay, choose, okay, so we choose 3 over 2. It implies that P 2/3 times 3 over 2 is 1. A at 3 over 2 over E at 2 over 3 times 3 is 1 is a constant. Done, okay? So that's it. So that's it with this example. All right.